action on symmetric space.
Thank you. So this is the second talk about this topic, and I want to just browse quickly through what we did 2 days ago, because probably many of you will have forgotten what I said, and I probably did. So there we are. So we discussed, I introduced what polar actions are to remind you. An action is polar if it admits a section, which is a submanifold, which intersects all orbits of the actions perpendicularly. Yeah, so this is the main topic of the talk, actions with this property. And the problem I'm talking about is that of the classification of polar actions on Riemannian symmetric spaces. And then I gave an overview of what is known in the compact case. So basically one has a complete classification for the irreducible case. For the non-compact case, one understands them for real hyperbolic spaces. I discussed briefly differences between the compact and non-compact case, that there's really a big difference between these two cases. This is an overview of where we are with the classification problem, and I started to talk about the homogeneity 1 case. So this is the special case where the section has dimension 1, which appears to be the most elementary case. So I was talking about this in the last lecture, and today I want to continue with this, and I want to also then talk a bit about the hyperpolar and polar case. Maybe to remind you of the setup, let me go back, because I'm going to use this again. So our symmetric space is G over K, where G is a non-compact semi-simple real Lie group, K is a maximal compact subgroup, O is the point which is fixed by this compact group, and H, by H we denote the connected closed subgroup of G, which acts on the space polarly. So this is our notation. And this result gives somehow the strategy for a classification of homogeneity 1 actions. I discussed the first case where the orbits form a Riemannian foliation, and I discussed the second case where we have a totally geodesic singular orbit, and I want to continue with the third and fourth case. So this is the case of canonical extension and nilpotent construction. So to remind you of the foliation case, we understand them. We have this parameter space. I discussed this for the hyperbolic spaces. I don't have to go through this now in detail. Examples, there we are. And totally geodesic singular orbits, where I explained this. Now the difficult case is the one of actions where one has a non-totally geodesic singular orbit. And what turns out to be a good concept in this context is that of parabolic subgroups and parabolic subalgebras. Now a parabolic subgroup, maybe I just say intuitively what this is for the real hyperbolic plane. So when we consider the Poincaré model for real hyperbolic plane, what we normally draw is a circle, but that's not the plane, it's just the disk inside, the open disk, which is a model for the real hyperbolic plane. And what are this? This circle is intuitively the boundary of it. Well, it's just when you view this really as a part of Euclidean plane. So the circle is the boundary. But one can formalize this in various ways. And one way to do this is you consider a point on the boundary as an equivalence class of asymptotic geodesics in the hyperbolic plane. So what I mean by is, so let's take this point here on the boundary. Then I have a bunch of geodesics in the hyperbolic plane, which are all converging towards this point at infinity. Yeah, in the Poincaré disk model, here is one geodesic, and then so I have then to draw other geodesics. So these are just arcs intersecting the circle perpendicular, right? So that's how we get all the geodesics. So that's it. Probably something like this. So we get this whole bunch of asymptotic geodesics, and one can define a point and the boundary as an equivalence class of asymptotic geodesics. Yeah? And this is a concept which one can generalize to more general spaces. Yeah? And so in arbitrary, say, Riemannian symmetric spaces of non-compact type, one can define a boundary by taking the sets of where a point is an equivalence class of asymptotic geodesics. Yeah? And then one has to put a topology on this, on the union of the space with all these sets of asymptotic geodesics. But this can be done in a straightforward way. Okay? So one can then, in this way, one obtains a compactification of the space. Now, when we look at the isometry group of real hyperbolic plane, so an isometry maps geodesics to geodesics. So in particular, asymptotic geodesics are mapped to asymptotic geodesics because distances are preserved. So every isometry on real hyperbolic plane extends then to an action on the boundary. Okay. So when we have something on the plane, that extends to an action on the boundary. So we have this action on the compactified real hyperbolic plane. And when we take then the stabilizer at a point on the boundary, this is what is known as a parabolic subgroup of the isometry group. Yeah, so parabolic subgroups are stabilizers of the extended action of the isometry group to the boundary. That's what they are geometrically. Parabolic subgroups. And one can describe explicitly, now I go back to the slide so we don't need the light anymore. There is a simple way of describing them algebraically, which I want to describe now. So we have the Lie algebra of the isometry group. K is the Lie algebra of the stabilizer, and the orthogonal complement with respect to the Killing form gives us this subspace P, and together we get the Cartan decomposition of the Lie algebra. Then we choose a maximal abelian subspace of P. Then the adjoint transformations with respect to elements in A are self-adjoint transformations, so one can diagonalize them. But since this is an abelian subspace, one can diagonalize all these adjoint transformations simultaneously, which leads to a joint eigenspace decomposition of the Lie algebra, which is known as the root space decomposition of the Lie algebra, yeah, which I write here. So 0, G0 is the eigenspace with respect to the 0, 1 form, and then here we've got the other, what the eigenspaces or root spaces. They're called root spaces for this. So what we get is a root, what's known as a root space decomposition of the Lie algebra. Sigma is the set of all roots where we have a non-trivial eigenspace. Yeah? And then one can find, this is just standard theory of such root space decomposition, a set of simple roots which I denote by lambda, which generates the whole root system. Okay? So this is then gives us somehow an algebraic description of the Lie algebra. Now to describe parabolic subalgebras, what we do is we choose an arbitrary subset of lambda. Now lambda is you see our symmetric space has a rank as a positive integer, which I denoted by r, and the set of simple roots has exactly this cardinality. So the cardinality of lambda is r, is equal to the rank of the symmetric space. Yeah? So that's a finite set. So we take now an arbitrary subset of this set of R elements. So there are 2 to the power R of such subsets. And we define a subalgebra by, we take the span of all these roots in our subset, and well, we intersect it with the span of phi, and we intersect it with sigma. So what we get is a subsystem of roots, a root subsystem. Okay? And we use this subsystem to define 2 subalgebras. So the first one is, we take the zero eigenspace plus all the root spaces corresponding to our subsystem of roots. This defines a reductive subalgebra of the Lie algebra G. It's straightforward, yeah? The other one is, here we take the sum of all root spaces corresponding to positive roots with respect to our choice of simple roots, which are not in our subsystem. This is a Nearpotent subalgebra, and then properties of root spaces tell us that L phi normalizes N phi, so then we take the whole sum. What we get is really a subalgebra, and this is a parabolic subalgebra. And really this is the Lie algebra of a Lie group, which I have defined there as the stabilizer of a point at infinity, point in the boundary. Yeah, this is how one constructs them algebraically. Yeah, and this decomposition is known as a Chevalier decomposition of the parabolic subalgebra, and one can show, and that's a fundamental result in this context, that every parabolic subalgebra of G is conjugate to Q phi for some subset phi of lambda. So one can really enumerate them. Yeah? So there are 2 to the power rank of the symmetric space of parabolic subalgebras, conjugacy classes of subalgebras. Okay. Now we needed a slightly more complicated decomposition. So our Lie algebra L phi decomposes into, it has a split component which I take off, and then the complement of this I denote by M phi. So the split component is always an abelian one, and M phi, so the complement of this is still, it's again a reductive subalgebra. And what we obtain in this way, this is an elementary construction, and what we obtain with this is what is known as the Langlands decomposition of a parabolic subalgebra. So M phi plus A phi plus N phi. We have a reductive subalgebra, an abelian subalgebra, and a nilpotent subalgebra. Yeah? So this is the end of the algebraic story, and now I want to explain what this means geometrically. So geometrically means I exponentiate everything, so we get corresponding subgroups. Yeah? Subalgebras define subgroups. So I want to explain what these mean geometrically. So when we take the subgroup of the isometry group corresponding to the reductive subalgebra M phi, we look at the orbit through our chosen point in the symmetric space. What we get is a semi-simple symmetric space for which the rank is equal to the cardinality of our chosen subset. Yeah? So we get a totally geodesic, this is semi-simple, so this is a totally geodesic submanifold of the symmetric space. And so this is a submanifold, but one can push this in a certain way towards infinity, and when one does this, one gets a boundary component of one of the other compactifications of a symmetric space, which was constructed by Satake, of the maximal Satake compactification. So you see what we do there is, in the hyperbolic space, in each direction we attach a point. What Satake does is he generalizes this in certain direction of the space. He doesn't attach a point, but he actually attaches higher dimensional objects to get a compactification. Yeah? And these are the objects he actually pushes towards infinity to get a compactification. So this is where these arise. So the reductive part gives us a semi-simple, totally geodesic submanifold of the symmetric space. So the abelian bit, we exponentiate the abelian the algebra, we get an abelian subgroup A phi of them, and when we look at the orbit through O, what we get is a Euclidean space in the symmetric space. It's the Euclidean space for which the dimension is the rank of the symmetric space minus the cardinality of the subset phi. Yeah, and that Euclidean space is also embedded totally geodesically in M. And eventually, so when we now take the L phi, see L phi is our reductive subalgebra, take the orbit through this, which I denote by F phi. This is just the product, Riemannian product, of our semi-simple, totally geodesic submanifold and the Euclidean space. Yeah? So we get really a simple product there. So the reductive group in the Chevalier decomposition gives us a totally geodesic submanifold of this kind. And then we have the Nearpotent part. When we exponentiate this, the Nearpotent part acts freely on the symmetric space. So in fact, the Lie group is really you can see this as a sub-manifold of the symmetric space. And when we put everything together, we get what is known as the horospherical decomposition, or as a horospherical decomposition of the symmetric space of non-compact type. Yeah. And this is not an isometry here, isometric one, because I mean this is an irreducible space. It's just a diffeomorphism. Yeah. And just to illustrate this again in the simplest possible situation, the real hyperbolic plane. So in the real hyperbolic plane, now our B phi in this case, so you see we have rank equal to 1. So what we choose, we don't have really much choice of phi. Lambda consists just of one point. Yeah? So our totally geodesic submanifold in this case is just a point. Yeah? The A phi, so we get a Euclidean space in there of dimension 1. So this is just a geodesic. And then the N phi, so this is the Nearpotent part. This gives us a horocycle in the hyperbolic plane. So this is this. Yeah? So the abelian bit gives us a geodesic. The N bit gives us a horocycle. And what this decomposition gives us is a set of nice coordinates on the real hyperbolic plane. Yeah? We take just now all the equidistant lines here and here. So here is one set of coordinate lines, and the other set of coordinate lines is given by all the parallel horocycles. It looks like this. Yeah. So what this horospherical decomposition gives us is that kind of a set of good coordinates for an arbitrary symmetric space of non-compact type. Yeah? That is a generalization of this picture for the real hyperbolic plane. Okay. Right. So now, what my result with Tamaro says is there are two possible, that every cohomogeneity 1 action on a symmetric space of non-compact type, which has a non-totally geodesic orbit, arises in two possible ways. One is through a canonical extension from a boundary component, and one is through some Nearpotent construction. And the canonical extension business is quite an elementary idea. So the basic example is think about Euclidean plane, and a very simple action there is the SO2 action on the plane. Yeah, what are the orbits? We get a point and the circles centered at that point. Yeah, so this is our standard polar action on the plane. And we can extend this in a canonical way to a polar action on the three-dimensional space on R3 by just adding at each point the line. Yeah? So we just pull this whole picture out along an axis here, and what we get is a polar action on the plane, yeah? Which is a trivial extension of the on 3 space, which is a trivial extension of the polar action on the plane. Yeah? And this is the basic idea for these canonical extensions. So what we do in the general situation, we have our boundary component B phi. This is a totally geodesic submanifold in the symmetric space, which has a rank which is smaller as the our given symmetric space. And we take an arbitrary cohomogeneity 1 action on this symmetric space. Yeah, so H phi is our group acting on B phi with cohomogeneity 1. And this, the isometry group or the identity component, is in the reductive part of the Langlands decomposition. Okay? So now what we do is we just add the abelian and nilpotent part in the Langlands decomposition. This corresponds now to the extension in this picture. Yeah, so here we just add an abelian part, the line. This is an abelian, one-dimensional abelian group. Yeah? And here for a symmetric space, it's just a bit more complicated. In certain directions, we add lines, geodesics. In other directions, we add horocycles. Yeah, but basically what we do here is just an extension. Yeah, the Langlands decomposition gives us an extension of the subalgebra. And what one then can show is that the corresponding group H acts on the symmetric space with cohomogeneity 1. Yeah? So starting from boundary components, so these are special totally geodesic submanifolds in the symmetric space, one can construct in a canonical way cohomogeneity 1 actions on the bigger symmetric space. Yeah? And what the result with Tamaru says is that if we have a totally geodesic singular orbit, then this action must arise in this way or through the second construction method, which I will explain a bit later. Yeah? But what this allows us for the classification is a rank reduction, because this totally geodesic submanifold has smaller rank than our given symmetric space. Yeah? So to some extent, these are not really new or interesting new actions. Yeah. So to give you one example, again here, because this is here, you're interested in two-plane Grassmannians. So we take here the non-compact two-plane Grassmannian. Yeah? So what does this construction method tell us for this particular space? The Dinkin diagram is again of type BC2 with corresponding multiplicities. So in this situation, our setup is A is a two-dimensional Euclidean space because the rank of this symmetric space is 2. Our root system, I've written this down here. So these are all the one forms defined on this plane. Then we have a set of positive roots. There are just 6 altogether. One can write down the multiplicities. All is known from these root space decompositions. And we have a set of simple roots here, alpha 1 and alpha 2, which give us this Dinkin diagram. Yeah, so this is the Dinkin diagram corresponding to this symmetric space. And that encodes really all the geometry we need for our situation. So this is our set lambda. And now we choose what are our parabolic subalgebras. Well, the interesting ones are really when we remove either alpha 1 or alpha 2, the simple roots. Yeah? So when we choose as a subset alpha 1. Now when we choose alpha 1, what does this mean? Alpha 1, we look at here. Here is alpha 1, our root, E1 minus E2. This has multiplicity 2. So the corresponding, so what is generated by this, what reductive algebra is generated by this, so we have just this root of multiplicity 2, but nothing else. So we just get this one root space plus a corresponding root vector. So this gives us a three-dimensional Lie algebra, and this is actually the Lie algebra of the isometry group of a three-dimensional real hyperbolic space. Yeah? That's what one gets from the root system. When we choose alpha 2 is E2. So what is generated by alpha 2? E2. So here we have E2, but we also have 2E2. E2 has multiplicity, where do we are here? Multiplicity 2 times n minus 1. 2 times E2 has the multiplicity 1. We have to add the corresponding root vector. So what we get, the corresponding reductive algebra, which is generated by this, is, well, I can see this, and if one is a bit familiar with this, it is the Lie algebra of the isometry group of n-dimensional complex hyperbolic space. So the corresponding boundary component is an n-dimensional complex hyperbolic space. Yeah? So for this this Grassmannian here, there are two boundary components, two non-trivial boundary components, a three-dimensional real hyperbolic space and an n-dimensional complex hyperbolic space. And what this tells us is, how do we get homogeneity 1 actions on this space? Take a homogeneity 1 action on real hyperbolic 3 space, or homogeneity 1 action on complex hyperbolic space, and then do this canonical extension process, and we get the homogeneity 1 actions on the Grassmannian. Yeah, and on real hyperbolic space, there are known, we know these all, these, it's well known. For complex hyperbolic space, well, they are also all known, because this was in my first lecture, where probably many of you didn't attend this, but here is a list of, see, they are all known. I don't want to go through this in detail, just to remind you that there is a complete classification, and to some extent it looks quite complicated on complex hyperbolic space, but I mean, extending these actions, yeah, so each of these actions can be extended to a homogeneity 1 action on the complex hyperbolic 2-plane Grassmannian. So in particular, I talk here about homogeneity 1 actions, but that's equivalent to talking about homogeneous hypersurfaces. Yeah, so what this method gives us is a large class of homogeneous hypersurfaces in the complex hyperbolic 2-plane Grassmannian, which are extensions of homogeneous hypersurfaces in complex hyperbolic space. Yeah, so there's really a big variety of such homogeneous hypersurfaces. And that's really in contrast to the compact case, where there are only two different types of homogeneous hypersurfaces. Yeah, that's what we encountered here several times already. Okay. So the second business is that of the Nearpotent construction. And this is the one which, I don't know, I don't really understand well. This is where we are a bit stuck. But I want to explain at least a bit, give you an idea of what the problem is here. Okay, so we have our set lambda. This is the set of simple roots, and these are simple. These are one forms on a vector space. So we have a dual basis in our vector space, which I denote by h1 to hr. So now we define. We make a special choice of subset by removing just one simple root. Yeah? So we take a subset of cardinality rank of the manifold minus 1. We just remove one root. So what we get in here are different parabolic subalgebras. Yeah? For each simple root, we get a parabolic subalgebra, and these are precisely the maximal parabolic subalgebras because we choose maximal subsets. So this is our, so I now use this notation here by the index j. I denote the corresponding parabolic subalgebra by the index nj, the corresponding Nearpotent group, and so on. Now the corresponding root vector hj generates a graduation, or gives us a graduation of the Nearpotent algebra, because if we evaluate a root in a positive root, which is not in sigma j plus, on our root vector, we get a positive integer. Yeah? So since we get positive integers, this gives us a natural graduation of the nilpotent Lie algebra, which one can show is just generated by the first bit, so where we get the value 1 when we evaluate. Yeah? So our root vector corresponding to our chosen root alpha j induces a graduation of the nilpotent algebra in the Langlands decomposition. That's all what happens here. Looks complicated, but it's not so difficult. Now what we do, assume that in our generating space of the nilpotent algebra, we choose a subspace V and define by njv the orthogonal complement of it. And this is a subalgebra of nj because V is a subspace of the generating part. So when we bracket, we come into the second bit or higher bits. So we always get a subalgebra when we do this. Yeah? Whatever we choose here, we get the subalgebra. And now we make two assumptions. The first one is that the normalizer of this subalgebra in the Lie group, in the reductive Lie group Lj, which arises in this Chevalier decomposition, acts transitively on this totally geodesic submanifold Fj, which is just the product of the boundary component with the Euclidean line. And the second assumption is that the normalizer of this chosen subspace V in the intersection of Lj with the stabilizer K acts transitively on the unit sphere in V, provided that the dimension of this subspace is greater or equal than 2. So these are two assumptions I make, whatever they mean. These are two assumptions, but when they are satisfied, then I can define a subgroup of the isometry group by we exponentiate. So we take the nilpotent subalgebra and exponentiate. We get a subgroup in Nj. And then we take the normalizer, this normalizer, which is a subgroup of Lj. We put everything together. So this is a subgroup of Lj, this is a subgroup of Nj. So altogether it's a subgroup of Lj times Nj. This is the Chevalier decomposition. So it's a subgroup of the isometry group. And this acts on the manifold with cohomogeneity 1. Yeah. So what the result with Tamaru says is every cohomogeneity 1 action with a non-totally geodesic singular orbit which does not arise through canonical extension arises in this way. Yeah, that's what we show. So one really needs to understand this a bit better. What does this mean? Yeah, in order to get a complete classification. And I want to give again one example. And I want to do this for one manifold. This here is it's a non-compact symmetric space G22 over SO4, which has real dimension 8 and rank equal to 2. One really doesn't need to understand what this manifold is geometrically, because one can describe it in algebraic terms. The only thing one needs to know really is the root system. And the root system of this manifold is of type G2. So I've written here, this is the Dinkin diagram corresponding to this symmetric space. So we have 1, 2, 3, 4, 5, 6 positive roots, alpha 1, alpha 2, and certain combinations of it. We have 2 simple roots, alpha 1, alpha 2. Yeah? So it's elementary linear algebra, what we now do here. So I remove the simple root alpha 1. What I'm left with is just alpha 2. Yeah? So what is generated by alpha 2? Well, we just have alpha 2 here. So let's do this. I go now to the construction here. Sigma plus. Here are our 6 roots. What our nilpotent algebra contains everything that is not generated by alpha 2. Yeah, so alpha 2, we have to remove alpha 2, but we have to see nothing else is generated by alpha 2, so we have to keep all other 5 roots. And now we get this graduation. What do we have on first level? So we have to evaluate alpha 2, I mean the corresponding root vector, on the remaining roots. So when we evaluate this on alpha 1 on H2, so what we get is just 1 as value. When we evaluate alpha 1 plus alpha 2 on H2, we get, well, what do I want? So I want to evaluate it on H1. So when I evaluate this here on H1, I get 1. When I evaluate this with H1, I get 1. So these are give us our generating space of the graduation. When we evaluate this here with H1, we get the coefficient 2. That's there. When we evaluate these 2 roots on H1, we get the coefficient 3. So there we are. Yeah, so there we get the graduation. It's a plane, a line, and a plane. And altogether we get the Nearpotent algebra, which is a 5-dimensional algebra. So now the reductive algebra in the Chevalier decomposition, this is the algebra generated by alpha 2 plus G naught. So we get these 3 root spaces, G minus alpha 2 plus G naught plus a G alpha 2. So if one puts them together, what one gets is a copy of SL2R plus a 1-dimensional abelian space. So that one can read off. And finally, when we take the intersection of L1 with the K, so we want to see what is the compact part in this one. So the compact part, there's nothing compact here. In SL2R, we just have an SO2. That's it. Okay, so we have an SO2. So now what we see is this SO2, K1, SO2, this actually acts transitively on the circle in this plane. This comes from root space, algebraic properties of root spaces. When I take this SO2, this acts transitively on the circle in this plane. Yeah? So when I now do this construction, I remove the whole space here, the whole generating space. Actually, our assumptions will be satisfied. So our Nearpotent construction method will produce a homogeneity 1 action, and one can write down the algebra explicitly. So we take here the algebra, the reductive algebra generated by alpha 2. So this is our SL2R plus R, plus we remove just the generating space and keep the rest, which is this bit. Yeah? So what we get here is a homogeneity 1 action on this symmetric space, which has a singular orbit. One can calculate this as of codimension 2, because this is just the space which I have removed. Yeah? So this is an explicit example for this construction method. Now, what strikes me is that we can only construct 2 examples through this method. Yeah? One is the one I've just described, and the other one is just a complex version of what I just described, where all the root spaces have dimension 2 rather than 1. So this is the symmetric space G2C, the complexification of the G2 modulo G2. We looked at other symmetric spaces. We cannot find any further examples, but we cannot prove that there are no further examples. So somehow we believe that there are no further examples, which would be a very good result if we can prove this. Yeah? So that's an open problem that we have at the moment, to understand this really better. But anyway, so the final conclusion is now all the homogeneity 1 actions, you see how well we understand them. Those which give foliations we completely understand. Those which have a singular totally geodesic orbit we understand. Those which come through canonical extension, we can say we understand. They're not really interesting because they come from lower dimensional symmetric spaces, so you can apply an induction method. So once you know them for rank 1, you can just continue to higher rank. Yeah? So it's really this bit which is the remaining problem. Understand this better. Okay? So this is where we are. Now I want to go to higher codimension. And the higher codimension, the first natural extension is that we look at hyperpolar foliations. So this is where we now allow a higher dimensional section, but we assume that the section is a flat submanifold. Yeah? We make this additional assumption. So here is a simple example of a hyperpolar foliation on Euclidean space. We choose a linear subspace of Euclidean space, and then we take all the parallel affine subspaces. And this, of course, gives us a hyperpolar foliation. Yeah? What does it look like in the plane? So we have here is our subspace, and then we take everything that is parallel to this. And what is a section? A section is just the linear subspace which is perpendicular to V. Yeah? So this is a section, intersects all the orbits perpendicularly, and it is flat. Yeah? This is the standard or the simplest model for a hyperpolar foliation. Okay. On hyperbolic spaces, now what I do is, let's choose an arbitrary hyperbolic space over one of the normed real division algebras. And there you encountered this already. Yes, 2 days ago, we have this codimension 1 foliation, yeah, which is given, which has a unique minimal leaf and then all the equidistant hypersurfaces. So this is another example. It's a trivial one. Now, what I want to explain to you is that all homogeneous hyperpolar foliations on symmetric spaces of non-compact type, whatsoever, whatever you choose, can be constructed from these two hyperpolar foliations. There is nothing else. These are the basic building blocks for all hyperpolar foliations on symmetric spaces of non-compact type. And the way to do this is using the horospherical decomposition. And that's what I want to explain briefly now. So we can construct another hyperpolar foliation on, we just take products. Yeah? I mean, that's an elementary construction when you have these foliations on irreducible components. You take products, then you get foliations also on the products in this way. Yeah? So we take a product of hyperbolic spaces here and the Euclidean space. We take these particular foliations here, the products of these. What we get is again a homogeneous hyperpolar foliation on the product. Yeah? So that's a straightforward construction. So in the next step, what I now do is we pick an arbitrary symmetric space of non-compact type, and we now choose an orthogonal set of simple roots phi. So by orthogonal, I mean that these are simple roots. The simple roots, they generate a Dinkin diagram. Yeah? Our simple roots generate a Dinkin diagram. Now, a subset of simple roots is said to be orthogonal if no two of them are connected by a line in the Dinkin diagram. Yeah? So you look at the Dinkin diagram of the symmetric space and you select just a few roots which are not connected in the diagram. This gives an orthogonal set. Yeah? It's again a combinatorial thing to do, to find all such subsets. Okay? And so we denote the cardinality of this set by K. We get a corresponding, now it's the same story again. This gives us a parabolic subalgebra, and here is the Langlands decomposition of the parabolic subalgebra. Now, the point of choosing an orthogonal set is that the boundary component, which is generated by phi, is just the product of hyperbolic spaces. Yeah? That's what it means geometrically. Choosing an orthogonal set of simple roots, the corresponding symmetric space which is generated by this is a product of hyperbolic spaces. So we get this product of hyperbolic spaces, and the abelian part we know generates a Euclidean space. Yeah? So this part here, m phi plus a phi, this part in the Langlands decomposition generates this totally geodesic submanifold in the, well, this is the bit in the horospherical decomposition which just omits the nilpotent part. Now on here we know we've just constructed this homogeneous hyperpolar foliation from our standard foliations, our building blocks. Yeah? So now what we do is we just add the nilpotent part in the horospherical decomposition to this foliation. So we take the whole nilpotent part. And what we get is a hyperpolar foliation on this space, and we just add this. Yeah? So we add a full space there. So this gives us a hyperpolar foliation on the symmetric space. Just mentioned here, for this particular choice, one actually gets the horocycle foliation, but maybe I should mention. And the main result is what we proved with Diaz-Ramos and Tamaru last year, is that when we have an arbitrary symmetric space of non-compact type, then every homogeneous hyperpolar foliation on M is isometrically congruent to one of these foliations I've just constructed. Yeah, which just comes from a basic foliation here on the Euclidean space and a rather elementary foliation on the hyperbolic space. Yeah? So it just has to put them together in a suitable way. Which is quite a nice construction and a nice result. Okay. So I want to give you one example. So we take this symmetric space, SLR plus 1R over SOR plus 1. This is the Dinkin diagram. So it's a simple Dinkin diagram. So now we use combinatorics. So we choose an arbitrary orthogonal subset. So what does it mean? We can choose, for example, alpha 1, alpha 3, and then the last one. Yeah? So we just have to make sure that they are not connected by a line in the Dinkin diagram. Okay? So we denote by K the cardinality. So what then the corresponding horospherical decomposition is, we get K products, K times K real hyperbolic planes corresponding to our choice of roots, times a Euclidean space of complementary dimension, so the rank of the manifold minus K, times some nilpotent bit. Yeah, this is how the horospherical decomposition looks like of this symmetric space. So we get K real hyperbolic planes, a Euclidean space, and this nilpotent bit. And then for this nilpotent bit, so what is this symmetric space? So these are like upper triagonal matrices with determinant 1. So n phi, one can write this in terms of matrices. This corresponds to the set of all upper block diagonal matrices with certain 2 times 2 and 1 times 1 diagonal blocks. Diagonal entries are 1. Yeah? So one can really write it down explicitly. So for example, if we take here's to be more explicit, SL5R over SO5, so we get 4 simple roots. This is our Dinkin diagram. So let's choose alpha 1 and alpha 4. Our horospherical decomposition of this space is then we get a product of 2 real hyperbolic planes, a Euclidean planes, and then a nilpotent algebra of matrices, which I've written down here explicitly. And this is how it looks like. So it's really explicit, this construction. And then, so go back to our thing, we have this horospherical decomposition. Now on each real hyperbolic plane, we select this foliation, a geodesic and the equidistant lines. So this foliation on this plane, this foliation on the next plane, same foliation on this plane. And then on the Euclidean space, we select a foliation by parallel affine subspaces, so a foliation of this kind. So that's what we put here. And there we just take the whole space. We select the foliation with n phi, and then the result with Tamaru and Diaz-Ramos tells us that the product foliation is hyperpolar on this space, and every homogeneous hyperpolar foliation on this space arises in this way. Yeah? So it's just a product of these foliations and such a foliation by planes. Well, hyperpolar, it means we have a hyperpolar action, and I'm assuming that the orbits form a foliation. We don't have any singular orbits. Yeah. So what this means, hyperpolar foliation, is we have a section which intersects all leaves of the foliation and intersects them all orthogonally. And this section is a flat manifold. It's a Euclidean space.
That means that over there, the first third line, in the right side decomposition.
Yeah.
Then your meaning is that meaning is for hyperpolar foliation.
This one here.
The right side.
The right side.
Yeah. All of the right side. So
this one.
Yeah.
No. This is the horospherical decomposition of. So this is a manifold. And this manifold is diffeomorphic to this one. And this is our decomposition we get from the Langlands decomposition and our special choice of roots, of orthogonal set of roots. Yeah, this gives us a geometric, somehow this set of coordinates on this space. Yeah, so this is the space, and these are the foliations here. And I put then everything together, and I get the foliation on the space.
Why the third line is named horospherical? Why it is named decomposition is named horospherical decomposition?
I think this terminology comes from Russian mathematicians in the 50s, 60s who investigated these things, and they called these horospherical, and they just went into the literature. And I think it comes from these because here, what you have in the Nearpotent part here, these are well, it's now called horocycles, horospheres. It has to do with the horospherical geometry. So these Russian mathematicians, they created this horospherical geometry of such places, and that's where it comes from. I imagine actually the it's probably a Greek meaning to this, also I don't know. Yeah. So this is how they all arise. So we understand completely hyperpolar foliations on symmetric spaces of non-compact type, or hyperpolar actions on symmetric spaces of non-compact type which give foliations. That we understand completely with this. We can describe them explicitly. What we do not understand yet is those which have singular orbit. We really don't even have an idea how to tackle this problem. Yeah, when there are singular orbits. So I have 6 minutes left. So this is actually quite an interesting remark. When we have an arbitrary symmetric space of non-compact type, and we choose an arbitrary parabolic subgroup in there, so remember we have 2 to the power rank of the manifold of parabolic subgroups, yeah? And then we take the Chevalier decomposition of this parabolic subgroup. Then one can show that the action of the Nearpotent group in the Chevalier decomposition on the manifold is polar. Yeah? So this is an example of a polar action. But its action is hyperpolar if and only if we choose as phi the empty set, in which case we get a minimal parabolic subgroup. Yeah? So unless we choose phi as the empty set, in all other cases we really get polar actions which are not hyperpolar. Yeah? And this is on every symmetric space. And this is what is really different from the compact case. Remember, this result by Kohlross and Litschak states that on a compact symmetric space of rank greater or equal to 2, every polar action is hyperpolar. Yeah? And this is not true in the non-compact case, and these are the most simplest examples of polar actions which are not hyperpolar, yeah? Coming from parabolic subgroups and the Chevalier decomposition. Yes. So maybe then to end with, I will talk about polar foliations. So now I go to the most general case, polar. Polar means that we have an arbitrary section, a totally geodesic section, which is not necessarily flat anymore. Yeah, this is the most general situation and the most difficult case. So we understand the case of foliations now for hyperbolic spaces. So the way to construct them is the following. We consider complex hyperbolic space as G over K. These are the corresponding groups. The restricted root space decomposition is of this form. We have just one simple root, alpha, but then also 2 alpha is a root. So this is our root space decomposition. We also have an Iwasawa decomposition. K is so we have the Lie algebras, the N. So the Nearpotent part in the Iwasawa decomposition is the sum of the positive root spaces in a restricted root space decomposition. So this is the Nearpotent part. So our complex hyperbolic space, when we factor out K, what's left is A times N, which gives us the usual solvable Lie group model of complex hyperbolic space, where we have a solvable Lie group equipped with a left invariant Riemannian metric. Okay? So now what we do is we choose V is either the trivial subspace of A or A. So V is either 0 or A. And we choose in the root space G alpha, well, you see, G alpha has complex dimension n minus 1. This is actually a complex vector space with respect to the complex structure on complex hyperbolic space. So this is a Cn minus 1. The G2 alpha has real dimension 1. So now what we choose is a real subspace of this complex vector space. And now what we do is we take the orthogonal complement of this real subspace in N and we add the complement of V in A. So A is one-dimensional. So this is either a trivial space or A, nothing else. Yes, 2 possibilities. So then this is a subalgebra of A plus N, which I denote by SVW, and then we exponentiate, we get then a subgroup of A times N. Yeah? So the Iwasawa decomposition allows us to or induces this subgroup. And what we proved a few months ago is that the orbits of this group action, they form a homogeneous polar foliation of complex hyperbolic space. Okay. So they are polar. So in fact the sections of this are real hyperbolic subspaces. Yeah, and their real hyperbolic subspaces are flat only when they are one-dimensional, but for higher dimensions they are not flat, of course. So we really get polar but not hyperpolar foliations here. And that's the main thing, every homogeneous polar foliation of complex hyperbolic space is holomorphically congruent to one of these foliations. So on a complex hyperbolic space, we fully understand what are the polar actions which give foliations. So this gives a classification of polar foliations or polar actions on complex hyperbolic space which give foliations. So we would like to generalize this idea to arbitrary symmetric spaces to see what can we say about foliations, polar foliations again. But again there we do not yet have the right idea for what the concept might be to generalize this. Yeah? So complex hyperbolic space is okay, but don't know. So I think I stop here. Thank you very much for your attention.